Welcome to Avalanche Breakdown YouTube channel, and today we'll discuss about camera sensor. Today is 15th of July and the table of contents are: what is a camera sensor, how does a camera sensor work, major components of a camera, types of camera sensors, camera output. We'll take an example: camera on an autonomous vehicle, applications of camera sensor, limitations of camera sensor, why camera sensors are important, what is light, properties of light, light in camera, light sources, electromagnetic spectrum, visible light, infrared, ultraviolet, why the electromagnetic spectrum matters, camera hardware, camera calibration, stereo camera, thermal camera, summary. So in this document, what we'll try to understand is the use of camera sensor, why is it important, and we will think of it in terms of autonomous vehicles. Yeah, and once we see different things, we'll understand the concept. So let us start. So first of all, what is a camera sensor? A camera sensor is a electronic imaging device that captures light reflected from objects and converts it into digital images or video. It acts as eye of modern electronic systems, enabling machines to perceive and interpret their surroundings. A camera sensor consists of millions of tiny light sensitive elements called pixel. Each pixel detects the intensity of incoming light and converts it into electrical signal. These electrical signals are then processed by an image signal processor, ISP, to generate digital image. Unlike human vision, a camera sensor does not understand what it captures. It only records the intensity and color of light. Computer vision algorithms and artificial intelligence are responsible for interpreting the captured images. Camera sensors are fundamental components in autonomous vehicle, robotics, smartphones, drones, surveillance system, medical imaging, and industrial automation. Right. So what is definition? A camera sensor is an electronic imaging device that converts incoming light into electrical signals, which are processed to produce digital images or videos for visual perception and analysis. Right. I hope this is understood. Then let us move on. How does a camera sensor work? The image acquisition process involves several stages. You get light from the scene, then it gets into camera lens, then you have image sensor, CCD or CMOS, then electrical signal gets generated, then you have image signal processor, and then you get the digital image. The lens focuses light onto the image sensor. Each pixel on the sensor measures the amount of light it receives. The ISP, the image signal processing, then perform image processing operations such as noise reduction, color correction, white balancing, and sharpening before producing the final images. Right. So what are the major components of a camera? So like lens, image sensor, image signal processing, controller, and memory buffer. So what does a lens do? Focuses light onto the sensor. Here, image sensor converts light into electrical signal. Image signal processing processes raw image data. Then controller manages camera operation and this stores image frames. You have communication interface, transfers images to the processor. Right. Types of camera sensors. What does camera sensors do? They convert light into electrical signals. Right. The two most common image sensor technology are CCD, charge coupled device, and CMOS, complementary metal oxide semiconductor. What are CCDs? They have like high image quality, low noise, high power consumption, more expensive, common in scientific and industrial imaging. What about CMOS? Like low power consumption, high frame rate, lower manufacturing cost, easily integrated with electronics, used in almost all modern cameras. Right. Today, nearly all autonomous vehicles, smartphones, and robots use CMOS sensors. Right. This is very important. Now, camera output. The camera provides digital images consisting of pixels arranged in two-dimensional grid. For example, you have like 1920 cross 1080 pixels, and then you convert it to RGB values, and then a digital image gets formed. Each pixel stores intensity value corresponding to red, green, and blue color channels. Right. Next, camera on an autonomous vehicle. So first of all, on an autonomous vehicle you have many sensors, right? You have, as we discussed yesterday also, we have IMU, LiDAR, radar, camera, like that. So today we are discussing about cameras. So why is the camera actually used for? What is it used for? The front facing camera captures lane markings, traffic lights, pedestrian, vehicles, traffic signs, road boundaries. The visual information is processed by computer vision algorithms to understand driving environment and make safe driving decisions. Applications of camera sensors. Camera sensors are used in numerous fields including autonomous vehicles, mobile robot, drones, industrial automation, medical imaging, security and surveillance, smartphone, virtual reality, augmented reality, agriculture, aerospace, marine navigation. Limitations of camera sensors. Although cameras provide rich visual information, they have several limitations such as sensitive to lighting condition, performance degrades at night, motion blur during fast movement, rain, fog, and snow reduce image quality, Shadows and glare effect detection cannot directly measure distance with a single camera. These limitations are often overcome through sensor fusion with LiDAR, radar and IMUs. This is what we saw yesterday as well, that what is a sensor fusion? What is sensor fusion? Sensor fusion is a process wherein you take data from 2 or more sensors and you just fuse them together so that the limitations of one sensor can be overcome by the advantages of the other sensor. That is what it is. So as we know that with the help of single camera we cannot find the depth, but in the case of stereo camera we can do so. So since single camera cannot find depth, LiDAR data can be fused with camera data so that we can get depth information as well, and camera will give us a very good feature rich video information, right? So that is what it is. Let us move ahead. Why camera sensors are important? Camera sensors are among the most important sensors in the modern robotics and autonomous system because they provide rich visual information about the surrounding environment. Unlike LiDAR or radar, cameras capture detailed appearance information including colors, textures, road markings, traffic sign, pedestrian and object. This information is essential for understanding and interacting with complex environments. Right, let us move ahead. Rich environmental perception. A camera captures much more than object positions. It also records color, texture, shape, road marking, traffic lights, traffic signs, lane boundaries, pedestrian, vehicles. This enables machine to interpret scenes similar to human drivers. So the more features we understand, the more we are able to interpret the environment correctly, and the more we are able to interpret the environment correctly, the more the better will be our control of the vehicle, right? This enables machines to interpret scenes similar to human drivers. Enables computer vision. A camera images serve as primary input for computer vision algorithm, enabling tasks such as object detection, image classification, semantic segmentation, instance segmentation, feature extraction. Visual tracking, depth estimation, optical flow. Essential for autonomous driving. Autonomous vehicles rely heavily on cameras for lane detection, traffic light recognition, traffic sign recognition, pedestrian detection, vehicle detection, free space estimation, road edge detection, etc. Without cameras, many of these tasks would be difficult or impossible. Cost-effective sensor. Compared with LiDAR, cameras offer lower cost, smaller size, low power consumption, higher resolution, easy integration. This makes them attractive for large-scale deployment in consumer and industrial application. Next, supports artificial intelligence. Modern deep learning algorithms require visual data for training and inference. Camera images are also used to train models such as YOLO, faster RCNN, SSD, mask RCNN, visual transformers. These models enable intelligent perception and decision making. Right. Next, wide range of application. Camera sensors are used in robotics, autonomous vehicle, ADAS. ADAS means advanced driver assistance systems, drones, industrial inspection, medical imaging, surveillance, agriculture, consumer electronics, smart cities. Importance in sensor fusion. Although cameras provide rich semantic information, they cannot accurately estimate distance under all conditions. Therefore, they are commonly fused with IMU, radar, LiDAR, GNSS, wheel encoders. This combination improves localization, perception and navigation accuracy. I hope this is very well understood. Now till here we have seen basic properties of cameras, what it can do, what it cannot do, what are its strengths, when can it be used along with other sensors to solve some problems. Now we will talk about more fundamental things like light, properties of light and etc. Let us move ahead. What is light? Light is a form of electromagnetic radiation that carries energy and enables humans and cameras to see the surrounding world. It travels as an electromagnetic wave and in some situation behaves as a stream of particles called photons. This dual nature is also known as the wave-particle duality of light. Visible light is only a small portion of the electromagnetic spectrum. Camera sensors detect light reflected from objects, and the intensity and wavelength of its reflected light determines the brightness and color of the captured image. Light travels at approximately 3 × 10⁸ meter per second in vacuum, making it the fastest known physical phenomena. What are the properties of light? Light possesses several important properties. Light travels in straight lines in a uniform medium. It can be reflected by surfaces. It can be refracted when passing between different media. It can be absorbed by materials, can be scattered by particles, carries energy, exhibit both wave-like and particle-like behavior. These properties form basis of optical imaging system and camera design. Light in cameras. When a light from a scene enters a camera, the lens focuses the incoming light. The focus light falls on the image sensor. Each pixel converts the received photon into electrical signals at electrical charges. The ISP, image signal processing, processes the signals to generate digital image. Without a light, the camera cannot produce an image. What are different light sources? Common light sources include sunlight, LED, incandescent bulbs, fluorescent lamps, laser sources, infrared emitters. Different light sources produce different color temperatures and spectral characteristics affecting image quality. Electromagnetic spectrum. The electromagnetic spectrum is the complete range of electromagnetic radiation arranged according to wavelength or frequency. Only a small portion of the spectrum is visible to human light, but cameras can be designed to detect other regions such as infrared and ultraviolet. That's why you have cameras which are called as infrared cameras, right? They can detect light in the infrared region. So you have broad range of electromagnetic spectrum like gamma rays, X-rays, ultraviolet, visible light, infrared, microwaves, radio waves. This is what it is. Now since camera, we are talking about visible light. So visible light occupies wavelengths of approximately 380 to 750 nanometer and includes all colors perceived by the human eye from violet to red. Violet has approximate wavelength of 380 to 450, blue 450 495, green 495 to 570, yellow 570 to 590. It is like VBGYOR, VBGYOR, right? The standard RGB cameras are designed to capture this range. This is very important. This is an RGB camera, and this is not what is it, infrared camera, or right, or ultraviolet camera. This is RGB camera. What is infrared? Infrared light has wavelength longer than the visible light, approximately 750 nanometer to 1 mm. IR cameras are useful for night vision, thermal imaging, driver monitoring, agriculture and industrial inspection. Ultraviolet light has a wavelength shorter than visible, approximately 10 to 400 nanometer. UV imaging is used in material inspection, medical diagnosis, forensics, scientific research. Very important. So you have, if we can say, ultraviolet, and then you have visible, and then you have infrared. So that is how the wavelength, the electromagnetic spectrum will look like. Why the electromagnetic spectrum matters? Different imaging applications require different portions of spectrum. For example, RGB cameras capture visible light. Near infrared camera enable low night vision. Thermal cameras detect emitted infrared radiation. UV cameras reveal features invisible to human light. Understanding the spectrum is essential when selecting cameras for robotics and autonomous systems. For example, if I have an autonomous car, then the cameras on the autonomous car can help me detect different objects during daytime, but during night time the same cameras may not be very helpful. So we'll have to have cameras which operate in different wavelength so that I can capture various features even during low light conditions. Next, let us talk about camera hardware. Lens. The lens is optical component that gathers light from a scene and focuses it onto the image sensor. Its design determine how much light reaches the sensor, how wide the field of view is, and how sharp the resulting image appears. A lens typically consists of multiple precision glass or plastic elements arranged to minimize optical aberrations and improve image quality. What is focal length? Focal length is distance between the optical center of the lens and the image sensor when the lens is focused on a distant object. It is measured in millimeters mm. Focal length determines magnification, field of view, perspective. General guidelines. Short focal length is like 4 to 8 mm. Wide angle view. Medium focal length is like 25 to 50, balanced view, and long focal length, example 100 mm and above, narrow magnified view. Autonomous vehicles often use wide angle lenses to maximize scene coverage. Right. What about field of view? Field of view is the angular extent of the observable scene captured by the camera. A wider field of view covers more area but with less detail, while a narrower field of view captures a smaller area with greater magnification. Types of field of view. You have horizontal field of view, vertical field of view, and diagonal field of view. FOV depends on both the focal length and the sensor size. We will discuss a lot about field of view when we talk about LiDAR sensor as well, because in LiDAR sensor the field of view plays a very important role, and we'll discuss field of view there when we are talking about the LiDAR sensor. Aperture. The aperture is the adjustable opening inside the lens that controls how much light enters the camera. It is expressed as an f number, like f by 1.8, f by 4, f by 8. Small f number, wide aperture. Large f number, narrow aperture. Aperture affects image brightness, exposure and background blur. Now, depth of field. A depth of field is a range of distances within which objects appear acceptably sharp in an image. Depth of field is influenced by aperture, focal length, sensor size, distance to the object. A large depth of field keeps most of the scene in focus, which is desirable for autonomous driving application. Now, distortion. A lens distortion causes straight lines in real world to appear curved in the captured image. So there are different types of distortions like barrel distortion, pin cushion distortion, mustache distortion. One thing you have to understand is, like, sometimes by mistake distortions are part of the lenses, and the image which we get are called distorted images. So we can use signal processing to actually get rid of those distortions. So that is also very important. ISP, image signal processor. The image signal processor ISP is a specialized hardware block that converts raw sensor data into visually accurate digital image. Typical ISP functions include demosaicing, white balance, noise reduction, color correction, gamma correction, HDR processing, lens distortion correction, sharpening, tone mapping, image compression. The ISP significantly improves image quality before the data is sent to perception algorithms. So the thing to understand is, like, whenever we have a camera sensor, we will have a camera sensing pipeline. So after the sensing pipeline, you have something called as a perception pipeline. So the goal of the sensing pipeline is to make sure that whatever is the output of the sensing pipeline, that data is so correct, is so good, that the perception modules, which has machine learning algorithms which can do object detection, object tracking and all those kind of things, if the task is to give an output so that it becomes easy for the perception algorithms to do object detection and tracking. Okay, but if the output of the sensing itself, if it is not correct, then the perception will not do a very good job. Right. After this, let us move ahead. Let us talk about now camera calibration. So first of all, why calibration? Every camera introduces small geometric and optical errors due to manufacturing tolerances and lens imperfection. Camera calibration is the process of estimating these parameters so that images accurately represent the real world. Calibration enables precise measurements, accurate 3D reconstruction and reliable sensor fusion. Checkboard. There are various techniques by using which we can do calibration. Okay, a checkboard pattern with known square dimensions is photographed from multiple viewpoints. Algorithms detect the checkboard corners and compute the camera's intrinsic parameters and distortion coefficient. This is the most widely used calibration method in OpenCV. So there are different methods by which you can do calibration. Checkboard calibration is one such famous calibration technique. Then Charuko board. A Charuko board combines a checkerboard pattern with Aruko fiducial markers. Advantages: more robust corner detection, partial board visibility is acceptable, higher calibration accuracy, better performance under occlusion. But in general, we generally use checkerboard calibration, and it is very famous, and you will find, even if you see documentation of OpenCV, you will find something there. It is increasingly popular for robotics and autonomous driving. See, in an autonomous driving, in any system, in any autonomous system wherein you are using different sensors, it is very important that you do calibration and understand and try to understand what are the basic inherent errors present in it. Now, intrinsic calibration. Intrinsic calibration estimates the internal characteristics of camera, including focal length, principal point, skew, lens distortion coefficient. These parameters are stored in the camera intrinsic matrix and are unique to each camera. Extrinsic calibration. Extrinsic calibration determines position and orientation of the camera relative to another coordinate frame, such as a vehicle, robot or LiDAR. Here the LiDAR, it computes rotation, translation. Extrinsic calibration is essential for multi-sensor fusion. See, there are two things whenever, right? The first thing is called intrinsic. Intrinsic means things which are intrinsic means these are the things which belong, which are related to the camera itself. Okay, extrinsic calibration is when a camera is used along with other sensors. So you will have to find the position and orientation of camera relative to another coordinate frame. This is what is extrinsic calibration is. Next, stereo calibration. Stereo calibration determines the geometric relationship between two cameras in a stereo pair. It estimates relative rotation, relative translation, and rectification transforms. A stereo calibration enables accurate depth estimation through triangulation. See, the first two calibrations are about a single camera. Okay, this is about a single camera. This is about a camera with different sensors. For example, a camera and a lidar, a camera with GNSS, a camera with multi cameras, in a multi camera, multi lidar, and a GNSS system. This is what this extrinsic calibration is all about. Intrinsic calibration is about finding the parameters, finding the errors in the camera itself. Stereo calibration is about a stereo camera. Stereo camera means it has two cameras and not one, and these two cameras are separated by a distance. We will see about stereo camera later in the document once again. Now, hand-eye calibration. Hand-eye calibration estimates the fixed transformation between a camera and a robot manipulator or another moving platform. It answers the question, where is the camera relative to the robot? This calibration is essential for robotic manipulation, pick and place operation, and vision guided automation. Why is this important? Because sometimes the camera and the hand, just like in a human body, the hand and the eyes are at a distance, right? So if suppose there is an obstacle, the distance of the obstacle from the hand is not the same as the distance of the obstacle from the eye, right? So since we have to understand this, right, the distance between the hand and the eye, so to find out that in case of manipulators, so we require this hand-eye calibration there. So here this calibration is essential for robotic manipulation, pick and place operations, and vision guided automation. Calibration errors. A poor calibration can lead to incorrect object localization, distance estimation error, misaligned sensor fusion, distorted images, reduced camera accuracy, poor autonomous driving performance. To maintain accuracy, cameras should be recalibrated after mechanical changes, significant impacts, or changes to the mounting configuration. Then stereo camera. What is stereo camera? Stereo camera is a vision system that consists of two cameras mounted on fixed distance apart, similar to spacing between human eyes. By capturing the same scene from two slightly different viewpoints, a stereo camera can estimate the depth of objects using principle of triangulation. Unlike a monocular camera which captures only a 2D image, a stereo camera provides both color information and depth information, enabling three-dimensional perception. This is very important. Working principle. You have left camera, right camera, left image. From left camera you get left image, from right camera you get right image. Once you have both the images, you do stereo matching, and then you do disparity calculation, and then you get depth estimation. This is very important. Objects closer to the camera appear at different position in left and right. This positional difference is called disparity. Using the known distance between the two cameras, called the baseline, and the focal length, the depth of each object can be computed through triangulation. Advantages. Depth. With the help of what are the advantages of stereo camera? Direct depth estimation, passive sensing, no laser emission, high resolution color images, low cost than lidar, useful for obstacle detection and navigation. Limitation. Performance decreases in low light condition, difficult to estimate depth for textureless surfaces, computationally intensive due to stereo matching, reduced accuracy for distance objects. So in general, what we can say is like stereo cameras are generally used for indoor applications, and lidars are generally used for the same thing for outdoor application. But in recent years, the capability of stereo cameras is increasing very well, because of which it is being used outside as well. Applications: autonomous vehicle, mobile robots, drones, SLAM, visual odometry, 3D reconstruction, warehouse automation, bin pick robots. Example: Intel RealSense D435i Z stereo camera, Oak D, and Bumblebee stereo camera. Now this is the last thing. Now we have reached to the last part of this document. Now we will talk about thermal cameras. What is a thermal camera? A thermal camera, also known as infrared camera, is an imaging sensor that detects infrared radiation, heat energy, emitted by objects instead of visible light. Every object with a temperature above absolute zero emits infrared radiation. A thermal camera measures this radiation and converts it into image representing temperature difference. Unlike conventional RGB cameras, thermal cameras do not require visible light to produce an image. Working principle: you have an object, infrared radiation, thermal sensor, you do temperature measurement, and then you make thermal image. Warmer objects emit more infrared radiation and generally appear brighter or in warmer colors depending on the display palette, while cooler objects appear darker. Advantages: work in complete darkness, detects pedestrians and animals at night, operates in smoke, fog and rain better than RGB cameras, measures temperature differences, improves light time perception. Limitation: lower image resolution than RGB, higher cost, limited color and texture information, glass and polished metal can produce misleading thermal readings, reduced effectiveness in very hot environments where temperature contrast is low. This is very important point to understand. Applications: autonomous vehicle, ADAS, night vision, search and rescue, firefighting, industrial inspection, building thermal analysis, medical screening, military surveillance, wildlife monitoring. Example: FLIR, Boson, FLIR Tau 2, FLIR A series, Teledyne, FLIR automotive cameras, SEEK thermal cameras. So basically, if you see comparison between monocular, stereo and thermal cameras, it will look something like this. Number of cameras: monocular 1, stereo 2, thermal 1. Image type: RGB, RGB plus depth, infrared. Depth estimation: no, because it is monocular. Stereo has yes, thermal has no. Night vision: very poor. Then stereo camera poor, thermal excellent. Color information: yes, yes, no. Distance measurement: limited, accurate, limited. Cost: low, medium, high. Computational complexity: low, medium, medium. Main application: object detection, SLAM and night vision. So this is very important, right? Camera usage in autonomous vehicle. Modern autonomous vehicle rarely rely on a single camera type. Instead, they use multiple complementary cameras: front RGB, stereo camera, thermal camera, surround cameras, driver monitoring camera, fisheye camera. So the thing is, even cameras of different types are used in autonomous vehicle, and they all have different functionalities, and the functionalities are written here. Okay. For example, front RGB camera, it is used for lane detection, traffic signs, traffic light, object detection. Stereo camera, depth estimation, obstacle detection, free space estimation. Thermal camera, nighttime, pedestrian and animal detection. Surround cameras, 360-degree bird's eye view, parking assistance. Driver monitoring camera, driver attention and drowsiness detection. Fisheye camera, wide angle coverage for parking and low speed maneuvers. By combining RGB, stereo and thermal cameras with LiDAR, radar, IMUs and GNSS through sensor fusion, autonomous vehicle achieve robust perception across a wide range of lighting and weather conditions. This is very important to understand. Now, what is the summary? That camera sensors are indispensable for modern intelligent systems because they provide detailed visual information required for perception, localization, mapping and decision making. Their ability to capture high resolution images enables advanced computer vision and deep learning algorithms to recognize objects, interpret environments and support autonomous navigation. Despite their limitation under poor lighting and adverse weather, camera sensors remain one of the most important perception sensors and are widely integrated with LiDAR, radar, IMUs, GNSS through sensor fusion to achieve robust autonomous operation. So with this, we have actually come to the end of this document. So yeah, so I think you understood what we were talking about. So in this document, we discussed about camera sensor, and we have discussed these things like what is camera and how does camera work, what are the major components of a camera, types of camera sensor, camera output, camera on an autonomous vehicle, application of camera sensor, limitation of camera sensor, why camera sensors are important, what is light, properties of camera, light sources, electromagnetic spectrum, visible light, infrared, ultraviolet, why the electromagnetic spectrum matters, camera hardware, camera calibration, stereo camera, thermal camera and summary. I hope you found this document very useful. Thank you. Thanks a lot.